Hello everyone, welcome to my presentation. My name is Tong. My project is to design a single-phase charger for electric vehicle battery. I have 5 parts in my presentation. The background of the project, the specifications that have to meet, the process of circuit design, the simulation result, and the conclusion. With the high degree of electrification of modern industry, people are now more and more inclined to buy electric cars. So it also puts forward higher requirements on power quality so that electric cars can be charged efficiently. In this case, an appropriate vehicle charging device must be designed. As the voltage transmitted by the state grid is mainly 220 volt, 50 Hz, the charging equipment should consist of at least 2 parts. One is an AC-DC converter, and the other is an isolated DC to DC converter. Power factor is an important index of power system, and also one of the criteria to judge whether AC to DC converter is qualified. The switch is introduced into the circuit, which improves the power conversion efficiency of the device, but also brings harmonic pollution and low power factor. Therefore, it is necessary to perform power factor correction for AC to DC converter to eliminate harmonics and improve power factor. The technology introduces an active switch into a conversion circuit, which enables the input current to follow the input voltage by controlling the on-off of the active switch. In this case, we can make the input current close to the sine curve and the power factor close to 1. The switching mode of FET devices is full bridge converters directly affect system performance from the perspective of smooth operation and system efficiency. In general, FET devices similar to the power converter backbone have nonlinear characteristics, and the influence of parasitic parameters is more obviously at high frequencies, thus reducing the smooth operation of system to achieve efficient transmission. Therefore, due to the number of topology field effect transistor switches, full bridge converter topologies have good power handling capacity and are therefore widely used. This is the specification of the project. For input specifications, the input voltage is Vin equal to AC 90 volts to 240 volts. The frequency is 50 Hz to 70 Hz. Power factor should be 0.97, and the input current THD should less than or equal to 5%. And the third, we have surge current protection for startup instant. Soft starts through resistive branch and main contactor control to reach the stable PFC output capacitor voltage without inrush current. For output specifications, output voltage VO equal to DC 240 volt. Maximum output power is Pmax equal to 3000 watts. Maximum output current is Imax equal to 10 ampere. Maximum output voltage ripple is 0.5 VPP. The output current ripple should less than or equal to 5%, and the load regulation should less than or equal to 1%. Charging control accuracy is current 0.5 ampere for current and 0.5 volt for voltage. There are many kinds of topologies of APFC. The typical topologies of APFC are boost, buck boost, choke, and flyback converters. Boost converters is most used because it has several advantages against other APFC circuit. When boost converter is the main circuit of PFC, it can only boost the voltage so that the circuit is working stably. The inductor L is charged when switch S is on, and when switch S is off, L is discharged. The AC input current is always the same with inductor current, so that input current is continuous. When implementing large power DC to DC converting and power factor correction, the continuous input current has its own advantage. At the same time, the ripple current is small when input current is continuous, so it reduces the processing requirements for the filter circuit. Because the source voltage of the switch is always zero, it's easy to control with switch. The circuit of APFC contains two parts. One is the main circuit and the other is the control circuit. The main circuit consists of a single-phase bridge rectifier and a DC to DC converter. In this circuit, capacitor gets discharged when the diodes are reverse biased and no current flows through. Then, when the cap voltage gets lower than the grid, diode conducts and the inductor current increases. And when the inductor current exceeds the load current, the capacitor voltage starts increasing. At some point, capacitor voltage exceeds the grid voltage again, and the diode stays on. That's the current is still flowing but starts decreasing. The capacitor voltage keeps increasing until the point where the inductor current is below the load current. After a while, the inductor current decreases to zero and the diode turns off. The capacitor continues to be discharged by the load. Through this rectifier circuit, the waveform output voltage will have obviously ripple and not enough to be regarded as DC. Also, the output voltage and the input current are not in phase. So the PI controller, which generates PWM to control the on states of the switching device, is necessary. The control model utilized in this process is called hysteresis current control, in which the variable we take control in this control mode is the range of the inductor current. The current reference IL will generate the upper limits Imax and the lower limit I minimum that are called the hysteretic band. When IL reaches I mini, the switch in the boost converter is turned on, and when IL reaches Imax, the switch is turned off. Moreover, in this control mode, the conducting time of switch S is constant, but the shutdown time varies. Then the switching cycle is not constant. The bandwidth of hysteresis devices decides the size of the ripple, which can be constant or in proportion to instantaneous average current. According to the principle, the controller circuit is designed as below. In the circuit, after comparing the output voltage with the reference voltage, the result goes through the PID controller. The output of PID controller and the rectified input voltage together go to multiplier, and we set the output of the multiplier as the reference of current feedback control. After comparing the reference current with the input detected current, the result goes into the relay block and control the on and off of the switch. The inductor is composed of a winding and a magnetic core, which plays the role of energy transfer, storage, and filtering, and determines the magnitude of high-frequency ripple in the input current. The design of the inductor is crucial to the performance, efficiency, and function of the circuit, and whether the effect of the inductor can be satisfied. Here is the process. Calculate the peak of the maximum input current. The maximum inductor current report delta IL allowed is 5% of the maximum peak inductor current. And calculate the duty cycle when the inductor current gets to the maximum peak when the input voltage reaches the peak. The input current reaches the peak with the maximum ripple current. Therefore, we should calculate the duty cycle when it is the minimum input voltage. When it is the minimum input current ripple is maximum. In order to guarantee that the input current ripple meets the requirement in that situation, we need to use the following formula to calculate the inductor when it is the minimum input voltage. Fs is set as 50 kHz. Substitute all the value gets. It is proper to set the value to the inductor as 1 mH. When selecting the output capacitor, the second harmonic current, the switching frequency ripple current, the DC output voltage, and output voltage ripple, and the hold-up time are considered. The total current through the output capacitor is the second harmonic of line current and the RMS value of switching frequency ripple current. In this formula, the hold-up time is set as 35 ms and the minimum output DC voltage as 350 volts. It is proper to set the value of the capacitor as 4 mH. This is an overall diagram of the APFC circuit. The figure of output voltage from the figure we can observe that in steady state, the ripple of the voltage is small enough to be regarded as DC voltage. In this input voltage and current figure, blue represents the current and purple represents voltage. We can see that surge current is largely decreased. From this figure, we can observe that the THD is lower than 5% and meets the demand. When the circuit operates at steady state, the value of active power and reactive power is shown. Use the formula, we can get the PF is 0.9999, which meets the demand. The circuit of PSFB contains two parts. One is the main circuit, full-bridged transformer isolated buck converter, and the other is a control circuit. According to Faraday's law, the function of the transformer is to deliver the voltage from the primary side. The isolated transformer is mainly designed for the characteristics of medium and high frequency noise. The medium and high frequency loss is the silicon steel sheet. Transformer is quite large, so it will not be induced from the primary coil to the secondary coil output, so it can reach a clean power supply. In addition, the conductive part of the casting is connected to the ground, which can reduce magnetic leakage and electromagnetic interference and ensure the safety of the output end. This is a circuit diagram of the full-bridge transformer isolated buck converter. The operation status could be divided into 4 stages, depending on the status of diagonal switches on or off. Through the switching status of the switches, the input voltage can be transferred to the output. This is a circuit diagram of the control circuit. The value of Kp1, Ki1, Kp2, Ki2 need to be set in the inner circuit of the phase shift module. As for the component selection, for inductor, calculate the input voltage of the buck converter in the right side, find the duty ratio of the MOSFET, use the formula to find the value of the inductance. It is proper to choose the inductor as 6 mH. For capacitor, it's proper to choose the capacitor as 400 μH, and the resistor is 53.33 ohm. The PI controller, as mentioned before, KI1 should set as 0, then just give KP1 a proper value as 0.018. As for KI2 and KP2, they should meet the ratio as, since in this case, it is the discrete system and the sampling time interval is 10 to the power of -7. The denominator term should multiply 10 to the power of 7. That is the ratio they really need to meet. So set, and this is the overall circuit of PSFB circuit and the control circuit. From the figure, we could observe that the current nearly constant at 7.5 ampere. When it gets the steady state to more specific, I use the cursor to measure the ripple. The maximum ripple equal to 0.0667%, which could meet the demand. From the figure, we can observe that the output power is lower than 3000 watts. At last, we can combine the two circuits together. Through the response time increases, though the response time increases, the output voltage still keeps constant when it gets the steady state, as the figure shown. The output current still it will keep at 7.5 ampere. The input current and voltage figure, showed that they are strictly in phase. In conclusion, first, the choice of component model and simulation are important to determine whether the device meets the requirements. However, there are still many problems that cannot be simulated in design and simulation. For example, the actual selection will be more difficult because there are many limitations, such as temperature and voltage upper limit, which may not happen during the simulation. Therefore, I should pay more attention and design more appropriate circuits when calculating components for simulation. Second, PFC circuits are very useful to ensure the power quality of the grid, and there are current control modes and voltage control modes, both of which are very useful and important. Third, PSFB can easily and quickly control the output voltage to the demand value. With the development of electric cars, such circuits will be more widely used. Thank you for listening.